My name is Miki Tebeke. I'm a developer, not a data scientist. I'm working with Python for, let's say, 25 years, give or take. What?
Forever.
Forever, yes. And Python is still alive, right? Python is 32, by the way. I haven't started that early. Mostly on the boundary between data science and production. On one side, giving information to data science or making data accessible. On the other side, running models in production. And this is where I'm coming from for this talk. Apart from that, writing books, making video lectures, and many other geeky things. Among them, I'm one of the organizers of PyData Tel Aviv. This is the first conference. So this is the PyData meetup. And we are going to have a conference a single day in Expo Tel Aviv, December 13. Ticket sales are on. We have a great agenda. We have great guest speakers coming over. So you're more than welcome. There's a discount code for if you're coming from here. We're also looking for sponsors. So all the companies that are saying that they're hiring, it's a great opportunity to put your booth in front of 400 people and show the swag that you have. Okay, so enough of the intro. Let's start talking, and I forgot to start the timer. Okay. So performance. When we talk about performance, especially in conjunction with data science, there are two things when we talk about performance. This is the performance I'm talking about, making things run faster, making it consume less memory. Right? The other performance, talking about the performance of the algorithm, the metrics that you choose, precision, recall, Cohen kappa, whatever you prefer. These are not these ones. We're going to talk about this optimization and why. So the first question is why? Why do we want to optimize the code? Right?
Just time. Time is a valuable resource.
Okay, so time is a valuable resource, but today, right, we have cloud, just throw more machines on it, you should be fine.
Cost.
Right, so cost. Yeah, so when we talk about performance, especially in cloud environments, this is cost. Right, if you consume less CPU, if you consume less memory, and then you can take machines which are costless, this is money. Right, the second thing that you mentioned is time, and time is not just time of the algorithm, it's also the time that your researcher is trying to run an experiment, and then maybe another experiment, and maybe another experiment. If each experiment is going to take a lot of time, it will really help the coffee vendors of the world, but I'm not sure about how people will be satisfied with what is coming. Another reason is viability of the code in production, right? Netflix, I said I'm old, right? So Netflix 2006 started Netflix Prize, which they said, here's our data. If you improve our recommendation algorithm by 10%, here's $1 million. This is before Kaggle, right? This is what started all this idea. 3 years later, one team, actually a few teams merged together and they won the challenge. But the algorithm itself never made it to production because it wasn't fast enough in Netflix scale. So it's really fun if you find something which is really, again, going to the other performance, really interesting performance in the metrics, but if it's not going to run in production, there's no business value, you basically wasted your time. So one of the things I'm going to try to do is convince you not to do optimization, by the way. So why shouldn't we optimize? There?
Pre-optimization.
Well, I'm not talking about pre-optimization, but
Development time.
right, so development time. Basically, there is a risk, right? Every time you do an optimization, the code is not that clear. It's usually more buggy. It's hard to maintain. So you're taking a risk. Every time you're doing an optimization, this is something that you need to be really careful about. So try to keep this thing in mind. When we're talking about optimization and we're coming to solve optimization problem, there's actually a lot of data, a lot of knowledge that we need to acquire. It comes from how the machine works, how the Python virtual machine works, how the networking is working, algorithms, data structure, how Pandas is built in, and many, many other things. So we're not going to go into every one of them, But every time you have an optimization issue, when you try to find out, you need to come out with a lot of knowledge. Maybe you acquire it as you go along. I do it for a living, so I have my bag of tricks, but it takes years to find that. One of the things is how the machine works. And a lot of time when we work with Python, right, we're at a higher level, we don't think about the machine below. We just, it's a VM, it's running, but still these things are affecting us. So this is computer latency at human scale. So you have the actual latency, which might be different these days from when it was published. I think this one was published 4 or 5 years ago, but the scale latency is about the same. So if you're saying that one CPU cycle is 1 second, if you're going to, so the computer is organized by CPU, it has 3 levels of caches usually where data is, then you need to go to the main memory, and after that it's going to the disk. Right, so if you miss the caches and you go to the main memory, it's about 4 minutes time, meaning the CPU now is going to wait about 4 minutes until it gets the data that it needs to operate, even if it's just increment. If you're unlucky and it's not in memory, and we need to go to the disk, this is about 17 hours, comparing to a single CPU cycle. Meaning that if our data does not sit in memory, if somehow we need to access the disk, this is a lot of wasted CPU that can do something else. And if you're going to the network, and below, right, this is a very long network call, right? It's across the US continent but still, 5 years, take it to months, even weeks, still there's a lot of time that the CPU is doing nothing. So if you can optimize at this level, and sometimes we go to these levels, in Python you can even affect how memory is aligned in memory. A lot of time it's done under the hood with Pandas and NumPy, but it's still something important. All right, so I'm going to switch to show you some code about the data. The data that I'm going to use is coming from the dataset you're probably familiar with. This is the New York taxi dataset. Just grabbed one file from there, and we're going to go. So I'm going to load the data, and just to see, we have 3.5 million rows, and we have several columns in our data set. That's roughly what we have, and this is what I'm going to play with. And because there's something with the screen, you're going to see my cheat sheet all the time. We are going to start actually with the rules of optimization cloud. Okay, and the rule of optimization cloud said you do not optimize. The first thing is Python is fast enough. The developers of Python writing low-level C, so it makes it faster. The developer of Pandas thinking a lot about algorithms, data structure. They use Python, so you do not optimize. The second one is the one that is really interesting. You do not optimize without measuring first. And I see 2 things here. One is, how do you know that we're fast enough? We need a number, right? We need to know that processing a day's worth of data should take less than an hour, a minute, a second, whatever. In my experience, getting these numbers from the stakeholders, business or production, it's really, really hard. But you can't go without them, because if you don't have these numbers, then you just optimize for fun, right? Because it doesn't have a business value. Once you know these numbers, now you can start measuring and say, okay, I'm hitting the target or not. And always make sure to have the business people understand that you're not going to hit the number all the time. Right? There are the percentages. You're going to do it 99% of the time, 99.9, etc. And every 9 is a lot of effort to do it. Okay. What happens a lot of time when I'm doing it, people are telling me, do it as fast as you can. Right? And my answer is usually, okay, you give me a hardware team in 2 years, we'll be there. This is usually not available, and then we start doing some negotiations about what can be done and how we can do it. So you need to get these numbers. A lot of time I start with saying, is a minute okay? Is a millisecond okay? By the way, a lot of time it's going to affect the design of the system. If you're doing fraud, and the requirement is that once you detected some anomaly, the client should be notified in an hour, in a day, in a minute, or in a second. These are 3 different systems you're going to build. So there is a lot of importance to these numbers. The second thing about measuring is to know where your code is spending the time. This is known as profiling. We'll see an example in a bit, but the idea is that you never guess. Every time that you're going to think, yes, my code is going to spend time there, from my experience, and I'm doing it, as I said, 20-something years, 50% of the time I'm wrong. I'm doing bad optimization because there's a bad guess. So I'm never guessing. I'm running the profile and looking at where the code is spending the time, and only then starting to access things. Okay. Number 3 talks about the external factors, going back to the previous slide about how much time things are taking. So if most of the time is spent on disk I/O or network, this is not a code problem. And then unit test. This is the risk that you're taking. I'll skip over the rest. Okay, so one thing is in IPython or Jupyter, we have these magics, right? So these magics start with a %, and there are 2 interesting magics that we can look about. One is the time magic that gives us just a single time of how things ran. So this is Parquet. Let's say that I want to read a CSV file. Yes?
Is there a possibility to move this a little bit to the left, because you can see all of the screen?
Oh. Okay. So, for example, and this is one thing that might affect your code. If you're reading from files, the Parquet is 318, and always note the units, right? 18 milliseconds versus 3.91 seconds, so about 10 times faster to load the same data set just because of the file, right? I hate CSVs with a passion. If you want to talk about it later, come and take me a lot of vent out about the CSVs in general. And the second thing that we have is known as timing. If I'm going to do a total amount, sum, this is going now to run the same code. In this case, it did 7 runs, 100 loops each, and reports both the time, the mean time, the average time, and the standard deviation. Okay, so this is something that you can run, these 2 magics, and depending on what you're trying to do, most of the time, if it's short snippets of code that run fast, you're going to use timeit, it's more accurate. But sometimes, especially when loading, you want to do more than that. If you have more than one line of code that you want to run, the magics in Jupyter actually can come with a single % sign. These are known as line magics, or with a 2% signs, and these are cell magics. And now it's going to measure what happens inside the whole cell, right? So you can, even if you want to have a bit of code, check out and see how it's working and what it's doing for you. And the last one that is interesting is the p-run. So the p-run, okay, hold on, scrolling is not mine. Okay, so now you can see it, right? So the p-run. P-run is a profile run. This is using the built-in Python profiler and generate reports about where we're spending the data. And when we talk about profilers, we talk about 2 kinds of profilers. The one that we have in the standard library is what is known as an event-based profiler. It gets information from the Python virtual machine, start a function, exit a function, enter a function, exit a function, and then you have a full view of what's going on. There are 2 disadvantages to this profile. One, the granularity is a function, right? So if you have a big function, and a lot of time in Jupyter cells and other things, we write a big chunk of code, even though we shouldn't. We won't see what's going on there. The second thing is that the overhead on runtime is bigger. Outside the standard profiler, projects like PySpy and others, there are sampling-based profilers. Like Aviv said, the same idea. There's something that wakes up every amount of time, ask Python, where are we now? And at the end, generates a report. Assuming sampling is fast enough, we are going to get an accurate reading of what's going on. When we see prun, you're going to see that it gets us actually three. One is the number of calls for the function. The second is the total time and per call time, and the cumulative time and per call time. So the total time is just the time spent inside the function. Cumulative time is the function and all this function it also called, all the call tree behind it to see that. So a lot of time when you're interested in profiling, what you're looking at is the cumulative time. You can do it in the same one again, and then you can see, and not sure how many people guess that get item from the frame is the number one issue here in the code, more than other things. Okay, there are other tools like SnakeViz and others that will give you a visual look at how where your code is spending the time, and they might be more interesting to look at. I'm old school. I'm using mostly this. Okay. So this is our code, right? It's doing a Followup. And basically, when we're talking about optimization and in Pandas, Followup is the enemy. We try to avoid Followup and we try to do vectorization as much as we can. And we just, if you're going to do the same operation in a group by, this is going to be about 10 times faster, a bit more. Okay, so always try to vectorize whatever you can. Sometimes you can't, right? But this is one of the things that we would like to look at. But if you have questions, feel free to ask them.
I have a question. I know there is a tool, maybe quite new, memory, like a memory profiler.
Yes.
System calls.
Yes. So there are tools. There are the built-in Linux Prof and other tools that they know how to track system calls and others. There's so many profilers out there, really. Just try them out, see what they say, whichever works for you. But yes, some of them tracking system calls. A lot of time, if your call is spending time on, let's say, waiting for a lock, threading lock to release, or maybe this is not going to be so obvious in other profilers, and then you need to look at system calls and other things as well. So yes. What did I do wrong now? Oh, I need just this one. So I'm just taking the first 10,000 rows, and then I'm doing a Followup with the iter rows. And this is one of the worst things you can do in Pandas. Pandas is column-oriented. It's not built for rows. You need to build a row every time you ask for it, because it needs to go to the column, collect the values, and get it there. And this is usually very slow. If you're going to do the same in a vectorized way, this is going to be much faster, right? Again, note the units, right? So these are 110 milliseconds, which are 100. Yes, I'm here. Okay, let's choose the fact that Python has underscore. So 319 times faster if you're doing that. So every time you see something that is doing iteration of the rows, that's one thing that is for sure killing your performance, and you should try look at something else. Another thing that we can look on is using functions. Okay, so this is the built-in Python Max which I'm running on the total amount, and this is one way we can do it, right? The other way we can do it is called the max from Pandas. But the more time it runs, it's better. It's also great in the winter. It really heats up your machine. So again, we're going faster. We can also call the NumPy, right? So if you do dot values, you extract the underlying NumPy array, and then you can call the max function. And then it's even faster. Okay, so knowing, and this is what I talked about, knowing how the Python VM works versus Pandas versus NumPy, and who's faster and who's better, this is always a thing to remember. There is a price to pay, by the way. So if I'm doing this, I'm going to get the sum. If I'm doing this, this is nan, right? So there is a big difference between NumPy seeing nan as an invalid calculation, and once it gets there, it's not working, versus Pandas with seeing nan as a missing value, and then it just ignores it. So you need to be aware, you gain performance, but the behavior might be a little bit different than what you're thinking you're going to do.
So when you compare nan,
yes,
compare NumPy, nan it will say true. You compare Pandas, it will say false.
No, so when you do some calculation, like sum or max, and there is a nan in the middle, Pandas is just going to ignore it, saying it's missing value, I don't care. And NumPy is saying, okay, I reached to something which is not a valid calculation, I'm stopping here, I'm returning a nan, that's it. There is a nan sum and nan max in NumPy that you can do all these operations telling it to ignore nans, but you need to be aware of that. If you're doing it naively like this, it might be an issue. Yes. NumPy, there's nan max? Yeah, there is. Wow. This is why I like working with Jupyter or IPython. All these questions, just write down and you will get an answer. Nan max is NumPy's version of doing operations ignoring nans, like Pandas is behaving. So it's roughly the same like it's faster than the Pandas one. By the way, you need to remember that in Pandas we have several types of missing values, not just nans, right? Not a time. There's the integer, new integer array, which has NA, and several other ones. So we need to look at this. This is not going to work. Okay. Another thing we want to look at is memory. Okay, so the data frame has memory usage, right? This is going to give you how much memory usage. I defined in the megabytes. So our data frame is taking about half a gigabyte, right? If you look on disk, right, this is taking way less from what we get inside the in memory. Pandas is really wasteful in memory. Okay, and the CSV is compressed, so make it, I don't know, 7 times bigger, but it's still not the what? Yeah. You think gzip on text? My experience is 30%, but maybe it's better now. I don't know. I think bzip is better. Not sure. Okay. So how can we avoid all of this? One is, we can just load what we need. We don't need to load everything into memory. And in Parquet and databases, this is much, much easier. We have less than what we. So this is one thing you can do. Just, it's really easy, right? Read CSV, read Parquet, boom, everything goes to memory. But sometimes, hey, I just need these two to work with them so I can reduce the memory. Another thing you can do, so we can look at the total amount, right? But if you look at the total amount a little bit better described, we can see that the values are between minus, I never get them wrong, right? So I just, again, the REPL. Between, and if you look at the D type, it is float 64, right? So float 64 can hold way more values than that. And if you're going to use float 30, not float 34, float 32, it is still in the range of the numbers that we want, right? So, yeah, float 16, I think the problem is that you can use, but it's not native to the hardware. So most hardware is, yeah, it has that, but I think the hardware is going to struggle with float 16. It's so ancient.
You know what network you use float 16.
Yeah. Really?
Yeah.
Okay, so maybe, right, so float 16 will get us even better. Yeah, they should be fine as well. So pick the data types, right? Sometimes when you load the data from Parquet, it already has a specific data type. When you load them from CSV, you can give D types to the read CSV, and it will help you with that. Okay, let's say we want to gather names. So we have these names, and now we want to assign to the vendor the name, the actual name of the, right? So we can use the apply with a lambda, but we don't need a lambda, right? We can just pass in the get method. Function calls in Python are expensive. So every time you can reduce that, and names.get is actually written in C, so we're getting better. And we can get even better with all right, with names. Right, so if we're doing the name, we're getting to 34 milliseconds versus the initial 21. Right, so 7 times faster. Again, understanding how pandas work and what's going on. If you look at the memory usage of the vendor, or the vendor ID, they're going to be about the same, which is interesting, right? Because one is a string, one is a number. They shouldn't take the same thing. And once you do deep equal true, meaning telling pandas not just look at the pointers, but go all the way, you will see the big difference between them. So we're gaining readability, we're losing memory. We would like to fix that. So one of the solutions that pandas give us is what is known as categorical types. If you don't have a lot of types in there, dot as type category. And now, if you look at the memory usage, it's actually better than the integer, right? Because it's encoding, it's doing like a hot encoding, encoding the numbers and saying them. And now we get actually the best of both worlds. It's consuming less memory, and the comparison, if you're doing comparison, actually comparison between integers, they're not equal strings and other things. Okay, so this is a taste of the things that I'm doing when optimizing Pandas to know where, but you first need to start with measuring and getting the goals. Now, the thing that is going to affect the most your team or your company is if it's in the culture. Once people start talking about optimization, maybe using a PyTest benchmark to publish benchmarks for running the algorithm and showing them when doing code reviews and saying, is this the base data structure for that? What is the requirement of performance for this one? And can you do as a company, can you tell me that a 15% increase or better precision is worth 5% decrease in performance? Can you do that? Most companies that I work with, they can't. They don't know, right? So think about performance, talk about that. You don't need to know all the algorithms and data structure, but once you start thinking about them, the internet is there, Stack Overflow is there. There's many things that you can learn from. So thank you. I have 2 classes in LinkedIn Learning. One is called Faster Pandas, which this is part of it, and Faster Python Code. Hit me on LinkedIn and I'll give you a free pass to watch them if you want to. Questions? Yes.
Yes, well, thank you very much. Interesting. Just a remark about teacher roles.
Yes.
You can use them. You can use teacher tuples.
Yes.
Same equals false. But times faster.
Okay, I haven't tried it. Yeah, most of the time that I had problem with iteros, I managed to actually do some kind of apply with the access equal 1, and usually it's good enough. More questions? Thank you. Oh yeah, Jacob.
That's a question, more like comments. You didn't elaborate enough about external tools to actually do Pandas. I can name a few: PyGenter, Bodo, Modin if you do things parallelized.
So there are several alternate data frames that are in play. The most famous, let's call it, is Dask, which can automatically parallelize a lot of computation. And there's Vue, there's Modin, there's several others. They are very interesting. Some use cases, they are better. The problem with all of them, there's actually also QDF coming from NVIDIA running calculation on the GPU. The problem with all of them, they're not 100% compatible to Pandas. There's always something that is missing. For example, in Dask, because they parallelize everything, you don't have a median function. Mean is easy to do in parallel. Median, not so much. So if you have a specific use case and maybe one of these are helping you, maybe yes, but I usually try them, and then I found out that most of the time it's just something is missing, and then it's not working. Yes?
You try to measure the time in PySpark for the same task.
This is moving from in the machine on a single machine, same memory space, to something that is parallelized. So PySpark, once you run out of all of these tricks and you need to move to more than a single machine to process the data, then tools such as PySpark, Dask, and others are the option. But you can still embed some profiling information inside of them. There's a way to run the profiler and the timer inside the running code and just publish it as metrics. If you do that, go and read about monotonic clocks, just to make sure that you're doing measuring right. Yes?
First of all, thanks a bunch. It was fascinating. Could you elaborate more about the apply with access.1? Does it not create a row for each?
No, I don't think so. I'm not sure. I'm not that expert on the internals of Pandas. I don't think it does that. I think it just goes for every column and then doing something. I'm not sure. Actually, it's a good question. I don't know. My answer is I don't know.
The uses I had
Yes.
is when you try to combine if statements and
Yes.
computations from
Yes. And when you manage to do that, it's usually a lot of times faster than doing a follow-up with literals. Maybe just the way that Pandas is running faster than Python follow. I don't know. I need to check it out. That's a good question.
This cooperation will be probably faster.
Not necessarily. Not necessarily. But you need to check it out. There are other tools like the JIT compiler, number, and sometimes even writing code in Python, which can also help with that. But this is a path I usually leave for last resort.
It doesn't always help.
No, it doesn't always help. No. Don't number all the things. It's not going to help.
Do you have any special tips about indexing? Like, I know sometimes if you saw the index, you do that faster.
The only thing that comes to mind is that I know that join data frame by index is usually faster than joining by specific columns. Apart from that, I don't have anything specific to indexing.
I think join is only by index and merge is by column.
Yes. Okay, so thank you very much.